Good afternoon, ladies, gentlemen. Welcome to Geological Society of London and our special public lecture. It is my absolute pleasure to introduce our today's speaker, Dr. Robert Hazen from Carnegie Institution for Science and George Mason University. Robert Hazen is a senior staff scientist at the Geophysical Laboratory of the Carnegie Institution for Science and Clarence Robinson Professor of Earth Science at George Mason University. Dr. Hazen did his bachelor's and master's studies in geology in MIT and received his PhD in earth science from Harvard University. Dr. Hazen currently serves as the executive director of the Deep Carbon Observatory, which is a 10-year research program supported by Sloan Foundation to study carbon in Earth. He's a fellow of American Association for Advancement of Science, the Geochemical Society, and the Geological Society of America. He has won numerous awards, including the 2016 Roebling Medal, the Mineralogical Society of America Award, and Mineralogical Society of America's Distinguished Public Service Medal. Dr. Hazen has published more than 400, not yet, maybe soon, 400 articles and 25 books on science, history, and music. Dr. Hazen's research spans a variety of topics, but today we are going to hear about his research on mineral evolution and mineral ecology, new approaches that exploit large and growing data resources to explore the co-evolution of the geosphere and biosphere. His topic is nothing less than the story of the Earth, how life, rocks, and the carbon cycle have co-evolved. Please.
Thank you so much. What a pleasure to be here to talk about the story of Earth. We live on a planet of breathtaking beauty. Seen from the proximity of our solitary moon, that blue marble with the swirling white clouds, and we look at it and we realize it's a dynamic world. It's a world of change. And we ask, has it always looked this way? Or has perhaps gone through different phases, different stages? And if so, what are those stages? Today, I'd like to explore this question and talk about how Earth has transformed repeatedly over 4.5 billion years, how life and rocks have co-evolved, and also how data-driven discovery can give us new insights to this question I think we're all fascinated by. This is an auspicious year for carbon, and I'm going to focus tonight primarily on the carbon-bearing minerals of Earth. This is, of course, 2019, the year of carbon at the Geological Society. It's the International Year of the Periodic Table, 150th anniversary of that document, and so carbon again plays a role. I'm proud that it's the centennial of the Mineralogical Society of America, and it's also the decadal anniversary of the Deep Carbon Observatory. So there are many events, there are many celebrations. This meeting is, of course, one of them, but we also have books that are being published, and there's videos. There's even, believe it or not, a carbon symphony by the British composer David Earl. It's not yet received its first performance. I'm excited, but the work is completed, and so this is all part of the year of carbon. And I am going to emphasize carbon minerals. And the reason I do this is because I'm a mineralogist. And one of the little things about science is we all have our specialties, volcanology or deep biology or diamonds or whatever. And so we see the world through those biased eyes. And nevertheless, I would argue that if we want to understand the story of Earth, its deep history, there's nothing better than minerals. Minerals survive through billions of years. There are even mineral grains that are older than Earth itself. So if you want to understand our planet, that's kind of a baseline. It's the ground truth, the testimony of the minerals. I'm also very excited that we're moving forward with this initiative, the 4D initiative. This is the next step in our studies. And right now, we had a workshop last June. We have about 60 different institutions that are involved. They're shown in this network diagram by the gray circles. There are also more than 200 individuals, geoscientists, bioscientists, planetary scientists, and data scientists all working together. And if you're interested in this new direction after the talk, please come and see me because I'd love to get you involved. Okay, I'm going to do three main broad topics related to planetary evolution. One is called mineral evolution. That's the study of the diversity and distribution of minerals through deep time. Mineral ecology, which looks at the diversity and distribution of minerals today over the planets. And in each case, it turns out biology plays very important roles in these topics. And then in order to understand minerals in a much more rich, multidimensional way, we're going to explore mineral network analysis, which is a way of looking at the co-relationships among many different minerals in different environments. These are all very new ideas, and the explorations I'm telling you about today have been done by my colleagues and myself mostly over the last 2 or 3 years. The objects of this are pretty obvious. We want to understand the evolution of Earth through deep time, and minerals is one way to do that. We're very interested in comparing Earth with other planets and moons because there seem to be distinctive parallel types of evolution. And finally, we want to understand the co-evolving geosphere and biosphere, rocks and life, because they do co-evolve. And all of these discoveries depend on data. Lots and lots of data, especially data related to deep time. So I want to pay homage to some of my colleagues who are doing the database development at the University of Arizona. rough.info/IMA is the complete official list of minerals. And they have about 5,400 species of minerals. You can go and look them up. You can search by chemistry or by structure. And we've also been building an evolution component of this, 185,000 separate data now on a mineral, a locality, and its age. Now, through this talk, I'm going to be mentioning this name mineral species a lot, and it may be a foreign term to you. It's kind of an odd concept, but a mineral species is defined as something that's naturally occurring. It has to have an n-member composition that's idealized. So, for example, here's a picture of quartz, SiO2. Well, quartz always has trace elements and other sort of defects, but ideally it's SiO2, and it has a crystal structure. So when I say there are 5,400 mineral species, I mean that there are 5,400 known unique combinations of an n-member composition and combined with a crystal structure. Okay, and so if you wanted to find where the minerals are, you go to mindat.org, partly crowdsourced by mineral collectors. It has over 1 million mineral locality pairs at this point. There's EarthChem, which has vast amounts of data on the compositions of rocks and other geological materials, run by Kirsten Leonard out of Lamont at Columbia University. PaleoBioDB, that's the fossil database. We have a protein structure data bank. That also implicitly includes deep time data. So there's all these resources that we're trying to integrate and use. So let's talk about mineral evolution. Mineral evolution is the idea that mineralogy has changed dramatically over deep time. And those changes are numbers. Partly it's just the diversity of minerals. How many different kinds of mineral species are there? It's also the distribution of those minerals, the relative abundances of them, the compositional ranges, because the trace and minor elements, the isotopic compositions also change quite significantly, and the grain sizes and shapes, something that most geologists have not paid as much attention to as I think we might want to do, because those sizes and shapes that look so beautiful in a museum are telling a story as well. We focus these days exclusively on the near-surface environment, the upper 3 kilometers, because that's what we can easily sample. It's what we're going to see on other planets and moons. And it's also what interacts with biology, and biology plays a huge role in this story. And the conclusion of mineral evolution is that new minerals arise at different times in Earth history through combinations of chemical, physical, and ultimately biological processes. So I have to comment on the word evolution. And some of you may have been a little uneasy hearing that word. You know, minerals, evolution, do those two words even fit together? And I would argue that they do. The word evolution has several meanings. It means change over time in the most basic, but it's been used in geology for more than 100 years. The evolution of the igneous rocks, we talk about the evolution of planets, the evolution of meteorites, various kinds of evolution. And so change over time is very much part of the geological context. It means something more than that as well. It means that there's an implication of a system that gets more and more complex, more diverse as time goes on. It also implies congruency, meaning that each stage of evolution follows logically from the one that came before. So there is a sequence. But I admit it is not this. So erase this from your mind. Minerals don't evolve in the Darwinian sense. That it's the suites or the ecosystems of minerals that change systematically, and partly because of biological evolution that occurs. So to give you a sense of what's different about mineral evolution compared to what came before, I asked this question. We have searched in vain in the literature for any mention of this question, even though it's an obvious one to ask. If you're a mineralogist, what's the first mineral? When did it occur? How long ago in the cosmos? Did it occur during the Big Bang? Well, I'd say no, it was much too hot, and there really weren't any atoms at the beginning. And when there were atoms, it was mostly hydrogen and helium, and they don't form minerals because they're gaseous, especially at those conditions. And then the hydrogen and helium formed the first generation of stars, and stars are much too hot to form minerals, but they start making other elements. And so I'd argue that the answer to the question of the first mineral in the cosmos has to do with these objects called supernovas, and the fact that you're producing lots of different elements, and you have an expanding, cooling envelope of gases. And as those gases expand outwards, you start condensing phases at very high temperatures from the most abundant element. Perhaps the most abundant in some of those envelopes was carbon, and the highest temperature condensate is diamond. So our speculation is the very first mineral in the cosmos was in the envelope of an exploding star. It was diamond precipitated from a vapor at very high temperature, about 4,400 Kelvin. As things cooled down to about 4,000 Kelvin, you could then precipitate the more stable form of graphite. That's the second mineral, perhaps. And then we have a whole series of others, prominent among them, silicon carbide, moissanite, another carbon mineral. And so carbon plays a very important role right from the beginning of mineralogy. These are the minerals, the minerals that are preserved in pre-solar grains, grains that are older than the sun and the planets themselves. The minerals have just a few elements, of course carbon, but about 9 others, so we have 10 different mineral-forming elements at all. And part of the question of mineral evolution is how do we go from a dozen minerals with just 10 essential elements to what we see today, 5,400 minerals with 72 different essential elements. That's the mineral evolution story. And so the solar system is born in a dense molecular cloud. The entire size of the solar system is much smaller even than the red dot in the middle there. This is a star-forming region with thousands and thousands of potential stars. The dust and gas here gets perturbed. It starts collapsing in on itself. It forms a nebula. And what you then have is a concentration of helium and hydrogen that concentrate in the middle, 90%, 95% more, gets gravitationally attracted to the middle. The rest, the dust and gas, is left over on the outside. There's not enough gravity to pull those together, but what happens is you get electrostatic attraction, and the dust particles actually come together like little dust bunnies. Like if you haven't swept under your bed in a while, you'll find these little clots and they're sort of loose. And then what happens is there are flashes of heat, both from the early star as it starts to form, and also perhaps nebular lightning. And you form little droplets as those dust bunnies collapse and melt. The droplets are called chondrules. And those chondrules then collect together to form the Chondrite Meteorites. There are about 60 different mineral species there, so we've gone from 12 minerals to 60. And then the chondrites start clumping together by gravity, and they form something the size of this room, and then the size of this building, and then the size of London, sometimes 100, 200 kilometers across. And when you get that large, you start getting other modifications. You get internal melting. You get separation of a metallic core with a silicate mantle. You get aqueous alteration from water. You get impacts, and shock minerals form. And all of these processes lead to a whole new set of minerals that are found in all the different kinds of meteorites that fall to Earth today, about 250 mineral species in all. So we've gone from 12 to 60 to 250, before even the first planet is formed. But then we have the formation of planets, the black Earth stage, where we have a planet coated by the rock basalt, that black rock, volcanic rock, must have been a very violent place at the surface. And in this stage, you start getting additional minerals. But if you have a dry planet like Mercury or perhaps like the Moon, it's really hard to see how we can get much above 300 different mineral species. However, if you have a lot of water around, you can then start forming some other things, hydroxides, clays, ices, and we think that these 420 minerals may be the endpoint for Mars or something that approximates it. So we're on Mars now with the Curiosity rover looking for minerals. We found a few dozen, but I suspect that if we really look hard, down the road we might find 400 or so on Mars. Stage 4, that's when you have a granitic crust. If it's wet, if it goes deeper down, or if it's heated from below, it can partially melt and produce a new kind of igneous rock called granite. And granite can concentrate many of these incompatible elements that give us a whole suite of really interesting minerals, boron minerals and lithium minerals, beryllium, tantalum, cesium, other sorts of rare minerals, about 500 new minerals in all that are found in pegmatites and granites. And so this is what we call stage 4. It gets us up to about 1,000 different mineral species. And Earth has another trick up its sleeve. It has plate tectonics, by which you rework millions of cubic kilometers of Earth's crust and upper mantle. And those fluid rock interactions, as we've heard in some of the talks in the last couple of days, can really select and concentrate elements. They can give you whole new mineral-forming processes. There are new modes of volcanism. There are new kinds of ore deposits, massive sulfide deposits, which carry hundreds of new sulfide and sulfosalt minerals. And you also have high-pressure minerals that come to the surface because of these tectonic processes. As mountain building crunches the crust together and new high-pressure phases are brought to the surface. So this gets us up to about 1,500 mineral species in all. 1,500 minerals that are formed by the result of physical and chemical processes alone. And yet, Earth today has 5,400, and the number keeps rising every year. How do we get to more than 5,000 species? And the answer is life. An astonishing revelation, one of the most amazing things of my career, because when I was a graduate student as a mineralogist, I was told, don't ever study biology, you'll never use it. Well, that's not true. Okay, so this is one of the intriguing things, the origin of life now. That's a subject that many people have been studying, and it turns out you have to use minerals. You have to use minerals because you simply can't do certain chemical steps without them. Sulfide minerals or clay minerals, maybe borates, things like that. They're used for protection of very delicate molecules. They absorb onto surfaces and are protected. They're used to catalyze new reactions at the mineral surfaces. They're used as templates to making larger macromolecules. Minerals play key roles in the origin of life, but the turnaround is that once you have life, then you can start making lots and lots of new minerals. And so here's the coevolution of the geosphere and biosphere, just based on the diversity of minerals. So let's look at the next 6 stages, all of which involve life. Stage 6 is the anoxic Archean biosphere. This is a period where microbes appear and that they accelerate the weathering, the alteration of rocks, because they get energy from those reactions. Now, they're not basically creating any new minerals as far as we know, and these are the culprits. These are the chemolitho autotrophs that do this. These chemical reactions, and so you have a redistribution of minerals at Earth's surface, but not a lot of new species. The real game changer is stage 7, and that's when photosynthesis comes into play. Those little microbes, the cyanobacteria that create an oxygen-rich atmosphere. And we think that this is gradually, it's a process that took maybe billions of years, but gradually added thousands of new minerals because of the near-surface oxidation of minerals that otherwise would just be in what's known as their more reduced forms. And you can see this on a grand scale. For example, the largest iron mines in the world were precipitated at this time as layers of iron oxides during a time of oxygenation of the oceans. So our hypothesis is about 2/3 of all the minerals that are known on Earth couldn't form in an anoxic environment. Therefore, those minerals are a consequence of biological activity. And we look at the lists of minerals. Most of the copper minerals, those beautiful blue and green copper minerals, they're all with copper in the 2+ oxidized state. Those seem to require an oxygenated atmosphere. Most uranium minerals, most manganese minerals, nickel minerals, iron minerals, cobalt, molybdenum, go on, and the list goes on, and there are thousands of minerals that simply cannot form without having this new, biologically induced mode of mineral formation. So here's one of our central themes of mineral evolution, that these changes in Earth's atmosphere, particularly what happened between 2.4 and 2.2 billion years ago, represent the single most significant factor in the diversification of minerals. We can move on. Stage 8, the intermediate ocean, about a billion-year period when the ocean gradually became more and more oxygenated from the surface all the way down to the bottom. It took time. It does not seem to have led to a lot of new mineral-forming environments. But it certainly was an interesting period, in spite of the fact that some people have called this the boring billion. Then there was a really dramatic period of a couple 100 million years when Earth seems to have gone through a few stages of global glaciation, where ice covered from the poles to the equator by some models. And in that case, what's the most abundant mineral on Earth? Crystal that has a structure? Ice, yeah, so ice becomes like the dominant mineral, and there may even be some mineral extinction going on at that point when other minerals couldn't easily form. So that's stage 9, and then we have stage 10. That's the final, penultimate, the ultimate stage where we see many, many other minerals forming because of a biosphere. Partly the terrestrial biosphere, the fact that plants have roots, this is 400 million years ago, the Rhynie Chert, Scotland, where you had about 1 centimeter long roots, but you start forming new clay minerals, other soil minerals. And today, of course, we have vast root systems that radically change the mineralogy of the land. There's also biomineralization, where we have minerals like carbonates and silica and other minerals that are formed exclusively by biological processes. And so here we see the story of Earth in 10 stages. And isn't it a nice story? And we're happy we can all go home now. Except, there's a problem here. This sort of feels to me like a just so story. It's very qualitative, waving my arms, saying things that sound like they might be true. But for a scientist, it's very unsatisfying. And when we first proposed this idea 10 years ago, it caught on rapidly, but those of us who were involved in that first paper were very uneasy, because there was no ground truth. There was no quantitative rigor to it. And so we've approached this in a new way. That's using data-driven discovery, using data to look at what exactly occurred when and where in ancient Earth and try to look for systematic patterns. So these large and growing data resources allow us to see Earth history in a much more rigorous way. So let's talk about the age of minerals. This is mineral evolution. And the ground truth here is data about a mineral locality, a species, and an age. And what you'll see on this diagram, on the vertical scale, are the number of mineral locality pairs in a given age bin, in this case 50 million year bins. And you'll see two trends here that are kind of the first order, the most gross scale trends that we see in mineral evolution. One is that it's episodic. There are pulses of mineralization. The second, and this shows the oxidation state in coloring, there's a change in the average oxidation state through time. And I want to just look at these two trends because they're really kind of significant. The first one has to do with the supercontinent cycle. The pulses of mineralization correspond to times when continents came together, the mountains were formed, and minerals are both formed and preserved in these ancient mountain belts. And so we see pulses of mineralization partly because of increased formation, but also because of increased preservation. You can see that very clearly when I show these vertical bars, which are at presumed times of the 5 big supercontinent assemblies in Earth history. And in each case, the highest peak over a billion-year span always falls under that period of supercontinent assembly. So that's one of the large-scale effects that we see. The other one has to do with oxygenation of the atmosphere. Manganese minerals are a particularly sensitive indicator because they occur in the reduced 2+ state, but also a 3+ and a very oxidized 4+ state. So Dan Hummer has put together lots and lots of information on manganese minerals. He's seen how they change through time. And what you look at here is the purple, the dark purple, is manganese in the more oxidized state. And there's a higher percentage, a systematically higher percentage of manganese 4+ towards modern history of Earth. So these are the kinds of trends we can study in great detail by getting these databases put together. And they're large, they're growing, it's still in an infancy of what we think we're going to be able to do down the road. We can show these in different kinds of graphical ways. Here, for example, are all the first row transition elements colored according to oxidation state. And you can compare and contrast different elements. You can see these trends, the tectonic trends, the biological trends, and other things as well that are hidden within these very rich data. We now have a complete periodic table with each one of these elements. This is updated regularly. You can go on our website, dtdi.carnegiescience.edu. You can pick out your favorite element. You can see what the latest data shows in terms of the distribution through time. So this is an ongoing effort. That's mineral evolution. And we see the large and growing data resources are putting kind of the meat on the bones of mineral evolution. We're able to see some of these specific trends. And we see physical, we see chemical, and we see biological processes at work. Mineral ecology. This is another approach, and this is where we're looking at the distribution and diversity of minerals across the globe today. And the objective here is to see if we can actually figure out a way to predict minerals that we haven't yet found or deposits that are yet to be discovered. And we employ, once again, comprehensive mineral data resources, and we employ statistical methods. Now, the key here is recognizing that minerals distribution over Earth follows a very familiar pattern. It's the same pattern as the distribution of words in a book. If you have a book, there are lots of common words, a, and the, and so forth. You'll find many, many examples of those, but many, many more words are rare, used only once or twice or 3 times in an entire volume. And you can use those rare words to predict, for example, an author's entire vocabulary. Even though a book only has a limited number of words, you can extrapolate on. And you do this by looking at the distribution of minerals on Earth. A few minerals are common, dominant in the surface of Earth. The feldspars, 60% of the volume of Earth's crust. But most minerals are rare. And those rare minerals follow a particular frequency distribution called a large number of rare event distribution. Here's what it looks like. When you look at this graph, what you're seeing on the vertical scale is the number of mineral species. In black is the observed, in red is our model for this, at exactly one locality. These are unique minerals found only one place on Earth. They're minerals found only 2 places. So there's about 1,100 minerals found in one place, 600 found at 2, and so forth, 400, 300, 200. As you get more and more localities, there are fewer species that are known at exactly that number of localities. And this is a very characteristic curve, large number of rare event distribution. The thing that's neat is you can do an accumulation curve, very familiar to biologists. An accumulation curve shows the number of different species you find as you keep looking at more and more individuals. So you go to a desert island you've never been to before. The first plant you come to is a new species. The second one is probably new too, and maybe the third. But then the fourth one is just like the first one, and the fifth one is like the second one, but then the sixth one is new. And so as you go along, you get more and more discoveries, but it kind of levels off. And you can predict how many things are missing. You can do this with individual plants. You can do it with DNA sequences. It's done all the time. We can do it with minerals. So on the horizontal scales, the number of mineral locality reports. On the vertical scales, the number of approved species. And when you start out, you find lots of new species, like if we go to Mars and start doing field work. But then you see more and more of the same thing over and over and over again. It starts leveling off. When we first did this analysis in 2014, we had about 4,800 minerals, 650,000 counts, and we can extrapolate into the future and estimate it turns out over 9,000 minerals actually exist. So that means there are about 4,000 mineral species yet to be discovered. So that's really exciting because we're actually saying what is the total mineral diversity on Earth, even though we haven't found it yet. And we can do games. We can say, okay, let's talk about specific elements. Let's look at carbon. There are 403 known carbon species from 83,000 mineral locality players. There's the frequency distribution. We can do the extrapolation. There's the data as of 2016. We predict there are 145 missing carbon minerals. And we can play this game in ever more refined characteristics. There, for example, are carbon plus hydrogen minerals. There are carbon plus calcium minerals, and we predict how many of those are missing. And we can even do this game in a kind of a backwards trick. We're really interested in carbon plus sodium minerals. But even though there are 100 of those species known, there's only about 1,400 species localities pair, and that's not enough statistically to determine what they are. But we can say, okay, well, let's look at carbon without sodium minerals. That's the others. We can do the extrapolation. It tells us that there are 82 missing minerals that have carbon but not sodium, and by subtraction we can say that there are 63 missing minerals that have carbon plus sodium, and in fact we can predict what some of those are. We look out, for example, at hydrous carbon sodium carbonates. There are 5 known, but synthetic chemists have made 2 others, and we can predict that those are very likely to be someplace on Earth today. They've been overlooked because they're white, they're crumbly, they're poorly crystalline, and they look like all the other hydrous sodium carbonates, so you have to really be lucky to pick out the right grain. So you go to places like Lake Natron or Oldonyo Glengai in Tanzania, and some of that white surface crust probably contains those missing minerals. Well, this has led to a really fun deep carbon observatory effort called the Carbon Mineral Challenge, where we're looking for the missing carbon minerals. We predict they're out there. Let's go find them. We've challenged mineralogists around the world, and they found about 20 so far. The first one to be found was a bellyite. That's one we predicted in this paper. Another one, parasite, we also predicted, but we didn't predict everything, and I have to confess, about half the minerals that are discovered are completely new structures, completely new to science. Their materials have never been seen before, and one of those is tenunculite. And the reason we didn't predict it perhaps will be evident to you when you see in detail. I don't know if you can read that. I will do it for you. It says tenunculite only exists when the excrement of a falcon bakes in the hot gases of a coal fire. All right, so we didn't predict it, but we did predict that there'd be 8 or so new organic minerals, and this, I guess, is one of them. So it's really been fun. And the conclusion for mineral ecology, this has just been so much fun. We can predict some of Earth's missing minerals, and this is a new thing. Mineralogy used to be you find what you find, and it's just like, whoa, we found something. But now we're predicting where to go and find it. The common minerals really define an Earth-like planet. But it's the rare minerals that help to make Earth unique in the cosmos. There's going to be no other planet, you can show that statistically, in the cosmos that will have the exact same mineralogy as Earth. And it also is possible that this L and Re distribution of minerals is a biosignature. It's a consequence of the biological alteration. I'm not sure we're going to see the same distribution of minerals, for example, on the Moon or on Mars. So, we've seen the distribution and diversity of minerals through time. That's mineral evolution. We've seen it through space. That's mineral ecology. We're interested in something more. We really want to understand in a much more higher dimension or a multidimensional way how are mineral systems interrelated to each other. And one approach that we can use that's both quantitative and rigorous is network analysis, mineral network analysis, which basically looks at minerals and their associations very much as social networks amongst human beings. So the idea is each of these nodes, these little circles or dots, is a mineral species. A link shows 2 minerals that coexist at some place on Earth or at some time. You can do this in whatever sort of context you want to, and you form a network. So think about a common favorite mineral like your granite countertop. You look at it closely and you see there's the mineral quartz, there's the mineral orthoclase, albite, biotite. They're coexisting, and so you can make a network of all the different igneous rocks that are out there, and you can draw granite. That's sort of the common minerals that exist in a granite. And you can draw this is all the igneous minerals here. So there's olivine basalt. You notice that it doesn't overlap at all with granite. There's nepheline cyanide. It does overlap a little bit, and so forth. All of igneous petrology is present in this one diagram. There are 37 points. That means it's in 36-dimensional space. And we're projecting it down into 2 dimensions. But there's a huge amount of information here about different kinds of igneous rocks. We can show this in a slightly more sophisticated kind of network diagram called a force-directed graph. In this case, each of these links is like a spring with attractive and repulsive forces, and you come up to an equilibrium state. You'll see how we can manipulate this in a moment. The node size for each of these minerals corresponds to how common that mineral is. The color, the spacing tells you how close or how far away you are, how commonly 2 minerals coexist. The color represents different groups of minerals. For example, red is quartz and feldspar. So we can look at this, and then you can go online with their dtdi.carnegiescience.edu. You can explore each of these manually, and you can move things around. You can see how each node is connected to others, and you can see how central it is. There, for example, is magnetite is connected to almost everything else on the network, because magnetite occurs in most different kinds of igneous rocks. We can use this for comparative network analysis of different planets. Here's Earth, Moon, Vesta, which is illustrated by the HED meteorites, and Mars. It turns out the networks have subtle differences, and we think that, once again, planetary networks may reveal, in some cases, biosignatures. That's something we're still studying. So let's look at a slightly more complicated network graph. This is one for 243 most common copper minerals, work done by Shauna Morrison, where we've colored these nodes by their chemistry. Red, then, are sulfide minerals like chalcopyrite. Blue are the oxide and carbonate. There's malachite, for example. And then yellow here are sulfate minerals, and there are a few others like native copper, which are in green. And the thing is, you can now manipulate this graph. Chalcopyrite's the commonest copper mineral. It's connected to almost everything else. It has a huge influence in the force-directed graph. Similarly, if you go to malachite, that's another very, very common mineral, and it also has a very strong influence. One of the things that surprised me, and my ore geologist friends told me, oh yeah, we knew that, was down there, green, that's native copper. It's smack in the middle of all the oxides and carbonates and so forth. I thought native copper would be with the sulfides. That's just my intuitive feeling, but it's not true at all. And so if you're a copper mineral specialist, you can spend days on this graph. 243 minerals, this is 242 dimensional space. It's how each of 243 minerals is linked to every other one. You can color it by various compositional. You can do it by age, you can do it by other sorts of factors, and learn a huge amount about coppers. And we can do this in 3 dimensions. Here's Dan Hummer's network for manganese minerals in 3 dimensions. You'll notice these weird nodes, these cluster, this little clump up here, mostly red, because these are divalent manganese phosphates from pegmatites. There's another little clump off to the side, and these are divalent manganese high-pressure metamorphic minerals. And then there's what we call a hairball. That's a technical term in the middle there, made of all the other things, most of the 3+ and 4+. And then you can manipulate this. You can rotate it. You can zoom in. And I'm going to let this play for a little bit because it's just fun. And if you're interested in manganese, this is the entire known suite of manganese minerals and all of their associations with oxidation state shown, but we could do this in terms of locality or paragenetic mode or many, many other kinds of metadata can be stored. You can click on any one of these nodes. You can find out lots of details about it. For example, all the localities where they occur, and you can link this to databases and so forth. So this is really powerful. Now for some even more bipartite networks. Bipartite networks show 2 different kinds of nodes. For example, the spread of a viral disease. Each of the black nodes has to do with a locality, perhaps an airport where people spread the disease, or a hospital or something like that. In this case, the individual colored are men and women, showing male and female. Well, we do the same thing with minerals. This is a bipartite network for carbon minerals. The colored nodes are minerals. The black nodes are localities where carbon minerals are found. And the size and color in this particular rendering both have to do with how abundant they are. So you see this cluster of very abundant carbon minerals down here. And then as you go up and out, you see somewhat less common. And on the outside, the periphery, you see all these very rare things that are found in only a few localities. This also has locality information as the Kola Peninsula, and quite symmetrical to it. The La Poudette Quarry in Quebec both have dozens of different carbon minerals, including many unique carbon minerals. Look at this interesting symmetry between the unique minerals in Kola, the unique minerals in Quebec, and then the 7 minerals that those 2 localities alone share. There's so much information in a diagram like this. It just boggles the mind. You could spend hours studying it. And one of the questions we have is, what is this topology of a network? No one has ever seen this topology before in network studies. This U-shape, this incredible thing where there's this flowering, beautiful flowering of carbon minerals coming out of the very core. I mean, what is this telling us? Well, we can look at this in 3 dimensions. We can indeed rotate this. It takes a bit for this to get going. There we're rotating it, and we're now looking at it. And this tells us that this U-shape of locality nodes, which are in gray in this particular 3-dimensional rendering, actually is like a vase shape. And you can see that even more clearly because we can do this with virtual reality. This is Shauna Morrison using, okay, this should play. That didn't play. Play for me, please. Oh, darn. Maybe in the booth we can see if we can click on this because it played before and this is the first time it hasn't worked. I'm sorry about that. But you would see this whole thing. You can actually walk into the network. You can look around and you can latch onto nodes and find out what they are. And what you see here is that the red nodes in this particular rendering are the localities, and they form this beautiful vase-like structure in 3 dimensions, quite extraordinary. I'd love to know what the structure was in higher dimensions. It's hard to think in those hyperdimensions, but there's got to be information. And, okay, I'm excited about this. You can probably tell that. But if you haven't been asking yourself deep down, well, okay, is this anything more than just pretty pictures? Is there any science here at all? Is there any reason why this is going to drive the science forward? And I'd like to give you 2 reasons why I think that's true that it is. First of all, networks embed information that you haven't included when you built the network. You'll see what I mean. And the second is there's something called affinity analysis. It's built out of network analysis that allows us to predict things that are missing. So look again at the copper network. You noticed how the clustering by composition was so strong. The only thing that was used to make this network was two minerals that either they exist together or they don't exist together. That's how you make the network. But there is embedded into this information on composition. That's the activity of oxygen. And you think about it, it has to be, because things that have very low activity of oxygen, very low oxygen levels, are going to form together, and things with high oxygen activity are going to form together. There's the sulfur activity. Again, things that form with very little sulfur versus a lot of sulfur are going to form themselves. And so naturally, a network, once you have it spread out like this, is going to embed information. Something else that's really amazing is timelines. We're interested in deep time. Now, you can imagine why in a paleontology network that might be true. This is a trilobite network. I love trilobites. Here are 6 of the orders. There's the Olenellids, the Tychoperids, the Asaphids, the Phacopids, the Lycids, the Proetids. And this is basically coexisting trilobite genera. But built into this is a timeline, going from very early in the Cambrian to the very end of the Paleozoic period. And that's true for any fossil network that you make. It has to be, because that's just the way evolution works. But look at this. This is that same bipartite copper network diagram I showed you before. And it's colored this time by the earliest occurrence of the mineral. And gosh, if there isn't a timeline driven in this. We're actually seeing mineral evolution in the context of the bipartite diagram. That's extraordinary. We have to think about what that means. But we didn't include any age information whatsoever when making this diagram. That's one reason why I think networks are going to be important, because they do embed information that we can extract. The second thing has to do with something called affinity analysis, or market basket analysis. It's a modeling technique. It's used widely. You have experienced this. If you buy a certain group of items, then you are more or less likely to buy some other group of items. I tried to buy Jonathan Lanine's astrobiology book on Amazon. There was only one copy. It was $300. I did not buy it. But within a second, they sent me this. If you like, you're going to like this. And this is a very, very complicated algorithm. It involves me and millions of other people, our buying habits, what we like, what we don't like, positive, negative correlations in very, very high dimensions. It takes incredible computing power. Entire buildings devoted to this sort of thing. And this is how, when you buy something, you get these responses. Okay, the same math applies to minerals. It's the exact same thing. You find a certain group of minerals at a locality, you are more or less likely to find other minerals at that or similar localities. You can do the same kind of market basket analysis. The mineral networks reveal those mineral associations, and we've been using this. So without going into a lot more details, let me just tell you about John Jan Roffen, our first real success. He loves the mineral wolfenite. It's a lead molybdate. It's a beautiful mineral. You'll see it in many museums. And he wanted to say, where could I go and find wolfenite where it's never been found before? And he did this analysis, and it turns out there's a place called Cook's Peak, New Mexico, which has a lot of different minerals, but wolfenite had never been reported there. And so he sent collector friends out to Wolf's Peak, and lo and behold, they brought back wolfenite. So that's really exciting. And we think the same kind of technology can be applied to the discovery of ore deposits. Think about finding the next big copper or cobalt deposit using market basket analysis. It's going to take big data resources, a lot of computational power, but we already have the United States Geological Survey and several mining companies wanting to work with us to try to get this thing going. So that's pretty exciting. So my conclusion of the story of Earth is that you can analyze, you can visualize this mineral data through space and time, and you find out the Earth's transformed, you find that life and rocks have co-evolved. And we can predict new minerals, something really, really exciting and new, I think, in mineralogy, that we can predict their localities and the types of minerals. And normally I would conclude there and thank you and ask for questions, but there's something new, and I have to share this. I have to share this. It's a little bit, maybe for some in the weeds, it's kind of a mineralogical thing, but it's exciting to me. Because for the last 160 years, mineralogy has been classified in a particular way, and I'm going to propose a new evolutionary classification of minerals. So remember what a mineral species is. It's defined by the International Mineralogical Association as a unique combination of composition and structure, both idealized. But what we've seen in the history of our planet is that minerals are not ideal objects. They're messy objects. They form as little tiny grains. They form as mineral scum. They form in all different kinds of ways, different modes, chemical, physical, biological processes. And what we're interested in evolution is not what mineral formed, but what mineral formed in what way. The current classification system does not do that. And so I think there are three problems. One is that some international mineralogical association species should be split into several different natural kinds. Another is that some of those species should be lumped into a single natural kind. And finally, a vast amount of Earth's crust is amorphous material, glasses, just messy soil stuff, which the IMA ignores completely because it's not crystalline. Those are problems if you're interested in planetary evolution. So what I'm going to propose is that we change the classification, or at least we complement the current system, which has been around for 160 years, with something that reflects modern data science. Think about diamond, the first mineral in the cosmos. The first grains of diamond are nanocrystalline, vapor-deposited diamonds, tiny, tiny specks that come to us in the form of chondrite meteorites. You dissolve out the rest of the meteorite, and what's left over is this mass of little diamond crystals. That's fundamentally different from type 1 diamonds, which form at high pressure, high temperature in Earth's mantle in an aqueous fluid that's saturated in carbon. And that's fundamentally different from type 2 diamonds, which form at high temperature, high pressure, deep in Earth, from a metal-rich liquid that's saturated in carbon. Those are different from the impact diamonds, like if an asteroid hits a dinosaur or something, you get these crystals of Lonsdaleite, as they used to be called. And then there's this thing called carbonado, and this is not advanced. There we go. Carbonado, which is this porous sintered diamond, and no one's actually really sure what it is. And there are probably 2 or 3 or maybe more other kinds of diamonds. So if you tell me, I found diamond, I want to know, well, what kind of diamond is it? What natural kind? That's what will tell us the context, the geological, the Earth evolution context of that mineral. Now, by the same token, tourmaline is a mineral group. You've probably got tourmaline or you've seen tourmaline jewelry. There are now, I think, 37 different IMA species based on N members. However, if you look at natural tourmalines, they really just have compositional zoning so that if you look carefully, you'll often find a single mineral grain that technically is 2 different species, or maybe 3 or maybe 4 species. No, but it's one natural kind. And so we need to be able to say, how many natural kinds of tourmaline? What kind of tourmaline is it, not what species? And finally, these amorphous materials, volcanic glasses, so fundamentally important to understanding Earth history and important to biology as well. Coal, it's not a mineral. It's just ignored by the IMA. And all of these kinds of near-surface materials that are very, very poorly crystalline, mixed phase, just messy, that get ignored, limonite, pyrolusite, they're just sort of terms of art for stuff that mineralogists throw aside and don't describe. Well, that's too bad, especially because now we've been to Mars, we look at the Curiosity data, and in some Martian soils, up to 70% of the soil is amorphous material, and we're just ignoring it. We're saying, oh, we found plagioclase, we found olivine, and that's like a tiny percent of the stuff, but we don't have any idea what the amorphous material is. We need to be able to describe that. And the way to do it is with big data. So we need people like Ross Large and Dan Gregory, who work at the University of Tasmania on this giant pyrite database, thousands and thousands of pyrite analyses that they did themselves, many, many different types of elements and isotopes and so forth. Our cluster analysis that we've just done, this is preliminary unpublished data, we used 12 of those trace elements that were common to several thousand pyrites. We did what's known as cluster analysis. There are many, many different flavors of cluster analysis. They're all sort of open access programs on the web. But we used something called Gaussian mixture model. And we came up with a fitting of that. And it turns out, when you go to these 12-dimensional states, this is a 3-dimensional projection, so it doesn't give you the full richness of the separation. But there are 7 distinct kinds of pyrite. So if we find pyrite on Mars, my first question is going to be, oh, that's nice. What kind of pyrite is it? Is it hydrothermal? Is it biogenic? Is it low-temperature alteration? Is it CDAX? I mean, these are all distinct kinds of pyrite. And from a classification, from an evolutionary point of view, that's what's important. So this is going to be the next 10 years of my life, if I'm lucky enough, working on this evolutionary system in mineralogy, starting from scratch, stage 0, the pre-solar minerals that form in stars, and working right through the whole thing. I think it's going to be a lot of fun. Because this, to me, is the true pathway to understanding the story of Earth. This incredible dynamic planet that we're fortunate enough to live on. We want to know its past. We want to know how we got to where we are today. We want to understand something about our uncertain future. and what we are doing to the planet ourselves. This is part of the story of Earth. And I think understanding the past will be key to being able to understand the present and the future of our planet. So with that, I thank you very much. I hope we have time for questions, and thank you again for coming.
Raise a hand if you want to ask a question.
In all the amazing amount of information you've given us today, I'm going to pick what will appear to be a minute part. And that is the graph in which you showed the progressive oxidation of manganese. Now, oxidation comes at a cost or a consequence, which is reduction. So the point is that that graph continued will show all the manganese oxidized.
Yes.
So what is the consequence of that change? What is not going to be reduced?
So there are two complexities which I didn't get into at all. One, of course, is the fact that on Earth, from the earliest times to today, in near-surface environments, there are extremely reducing conditions where the most reduced possible minerals occur. Microbes find this out because there's some microbes that must live in those reduced environments and others that live in more oxidized. The difference is not the most reduced parts. It's the fact that we've had progressively more oxygen in the atmosphere and therefore a stronger and stronger gradient, a redox gradient. But you're absolutely right. Redox reactions have to do with the transfer of electrons. And so something that's gaining the electrons, but something has to lose the electrons. And so that's part of the photosynthetic process. I mean, what life does, of course, is it reduces carbon, and that's what they gain electrons, and then the environment around it loses electrons. So I think that's folded into your question, but it's certainly true that when you see more oxidized species, what you're seeing is a manifestation of the increased redox gradient that exists at the surface. That's what we're seeing.
I think I caught somewhere in your talk the mention of the start of life and minerals and protection and catalysts. I wonder if you could say a bit more about that.
So the question of origin of life is one that still, of course, is unresolved in detail. But I think in principle, we do understand that for the origin of life, you need several key ingredients. You need to have an aqueous environment. You need to have carbon-rich molecules. You need to have some source of energy. You need to have a way of selecting and concentrating molecules to a small enough volume that they actually can interact. And so I think that the take-home message for minerals, and the reason that they have played such an important role in recent thinking about the origin of life, is that minerals provide several things at once. Minerals can have surfaces that attract organic molecules and concentrate them. In fact, selectively concentrate them. You can have surfaces that collect only the left-handed molecules. You can have surfaces that collect only the right-handed molecules. So you can have local environments with very special chemistry where the molecules are brought together, and then these surfaces themselves can basically help you move electrons to form chemical bonds. So I think that that's why minerals have brought into play. The details of the origin of life, there are many, many different scenarios. There are many, many different ideas for exactly which molecules and which mineral surfaces and so forth. To me, I step back a little bit from that and see the overall contributions that minerals can play in terms of chemical processes.
Who named Hazenite?
Oh, one of my former postdocs was kind enough to do that. Hazenite is an interesting mineral. It's one of those minerals found in only one locality on Earth. It's found in Mono Lake. Mono Lake is a very phosphorus-rich environment, and when it's dry for a period of time and the lake evaporates, the phosphorus levels get so high that it's actually poisonous to the microbes, I'm told. And so some microbes precipitate, they get rid of the phosphorus in the form of these beautiful little crystals, It's essentially microbial poop. So hazenite, it's the entire world supply of hazenite are a few little crystals that could be held in a thimble, and every time it rains, they all go away, which is sad. A colleague of mine has said hazenite happens, which I think is about, that's maybe my epitaph. but I love it. I'm just very proud to have a mineral named after me. Yeah, even microbial poop.
Over the billions of years, you said that the minerals have gone through, was it 10, 11 stages of evolution? Do you envisage that there will be any more stages in future time?
Of course, the 10 stages, I mean, that's a nice round number, and I suppose other people who did the same thing would have said there were 8 or 12 or some other number, but it worked out. Yes, stage 11, we've actually written a paper which addresses this fact, because many, many people are talking about the Anthropocene, or the Anthropocene, depending on how you wish to pronounce it, the human age where we've really affected the environment. And it turns out there are many minerals, hundreds of minerals, that occur only because of human artifacts. Mine tunnels where the walls have very specific environments that allow new minerals to form that have never formed before. Slag heaps, ancient artifacts. And of course, all the synthetic things that we do, which don't officially become minerals because if you synthesize them. But nevertheless, a billion years from now, if all of our societies and our cities are buried under layers of sediments, there will be things to preserve, the crystals and YAG lasers, specific kind of garnet, which is not a natural form. Those garnet crystals will survive. Other sorts of minerals and rocks that we humans synthesize will preserve. So there will be a distinctive layer, mineralogically speaking, stage 11, if you will.
Thank you for a fascinating talk. I was intrigued by the network basket analysis and the extrapolation of that to exploration in terms of mining. Can you say anything more about that and how fast it might move and what kind of traction? I mean,
Oh, there's an object lesson here, and someone who's a better philosopher than I can write this up. Yes, all the mining companies want this. They're desperate for it. The only way it works is if everybody shares their data. Okay? If you have every mining company on Earth say, here's what we've learned from these 100 porphyry copper deposits, then you'll be able to go to an unexplored porphyry copper and say, here's where we sink the well. We have a 99.8% chance of finding it. What they do is they come to us and say, we have all the data that we can possibly have on this new porphyry copper deposit. Tell us where to drill. And we can't do it. But in terms of the open access, things like discovering wolfenite localities, we can. And so it's a matter of changing the culture if everybody shares. Now, there are countries where you have to share. Australia is incredibly good at this. Basically, every mine that's on government land, all the data that's involved in that has to be shared, so that there's a place where we think we may be able to make inroads. And we're working very, very closely with the Earthbite Group, sponsored in part by the Deep Carbon Observatory. Dietmar Müller is Ibn Zaharovic, and they do the G-Plates platform, the Earthbite platform, and they're putting together an Australian collaboration to do exactly this. And I'm so excited, I can't wait to see what they find.
Thank you for a really interesting talk, which I can just about keep up with. But you touched on prediction. I mean, just thinking about other planets, say an exoplanet, could you imagine building a model where you could say how it might evolve, or are there so many elements and chaotic factors which would make that very difficult?
I think one of the most exciting frontiers in planetary science is doing exactly what you're describing. And we've been talking with scientists. I can't say it's gone very far yet because this is very much in its infancy. But with, for example, Arizona State University, there's a group at Rice University sponsored by the Deep Carbon Observatory. There are other groups that are very interested in saying, what if you had a planet that didn't have quite the same composition as Earth? The magnesium-silicon ratio changes. The carbon-to-oxygen ratio changes. How would that affect the planetary mineralogy on a large scale? Would you have a diamond-rich mantle that couldn't convect? Would you have a mantle that was entirely made of a mineral called pyroxene? When it melts, the first melt, unlike olivine, when you melt olivine, the melt sinks, pyroxene, it rises, and so you can form a crust. But if you had a mantle made of other materials, you'd have very different dynamics. And that's the kind of question. So geodynamicists, mineralogists, petrologists, people thinking like those of in the Deep Carbon Observatory about the whole global carbon and other volatile stages. Would you have plate tectonics? Can you have life on such a planet? It's really, and what do we mean by an Earth-like planet? Does an Earth-like planet have to have plate tectonics? Does it have to have the same major element ratios? It isn't just size and density, which what astronomers mean when they say, oh, we found an Earth-like planet. They're not necessarily meaning what some of us would think. So that's a very profound question. Yeah, and I'm really, I think you'll see many, many more papers about this in the next decade.
Rising out of an answer you gave just a while ago, the life origin thing, you seem to imply that the origins of chirality came about from the minerals. I mean, could you expand a bit on that? I mean, how do minerals cause chirality?
So chirality is this property of life where many molecules come in mirror-related pairs, left and right hand, amino acids that make up the proteins in your body, the sugars that are part of your DNA and RNA, they have either they're exclusively left-handed or exclusively right-handed. And the question is, where did that come from? Is it something that's built into the very fabric of the universe, that there are certain handedness? The CP violation of parity violation and particle physics, I'm told, gives you electrons that spin one way but not the other way. Maybe that trickled down and became the chirality of the planet. Or maybe it's just a chance thing. But the fact is, minerals give you one of many, many, many different ways to have local chiral imbalances. And to me, that's the key. As long as you have a local environment where you have a preponderance of left-handed or right-handed, by whatever technique you want to do that, then you have an environment where you can do certain kinds of chemical reactions you can't do otherwise. So all we're doing with minerals is demonstrating that's one more of many, many ways that chirality can be induced. The chirality question is unresolved, but it's not a difficult problem. It's an easy problem that has many solutions.
Okay, thank you very much. I think we should move next door for coffee now. And so if you do have any more questions for Bob, please find him at coffee. And we should thank him one more time.
Thank you.
So after the coffee break, the Janet Watson meeting will begin again at 4:20. And we do ask that if you're not involved in that meeting, you begin to make your way out of the building at that point. Thank you very much.